the fog. And so that cooling trend will cause the fog to stop being pulled onto land, and we'll get a period of warming. And you get your 3 to 5 sunny days in the summer when things get nice and warm, and then it warms up, and the cell starts flowing again. And then the fog is pulled on, and we get another few days of fog. And it cools to the point where the cell breaks down, becomes warm, and it pulls it again. And you get sometimes very nice cycles like that. Now that fog that's typical of us here is set in the context of a Mediterranean climate. This is not a Walter diagram, this is just a diagram of rainfall here. So the amount of rainfall per month across the year. You know this. This is the rainy season. The winter, our winter, is the rainy season in the Bay Area. And we can get quite a lot of rain in January. It starts to taper off in February and March, and it goes to almost zero in summer months. But check out fog. What happens to fog across the year? Well, it's low. The amount of fog is low when it's raining. And it starts to ramp up in those summer months, precisely when the rain is stopping. Hello. So fog levels peak when rainfall is lowest. The dry season is the fog season. And that's different than some other Mediterranean climates that don't have fog. We have fog forests here in California as a result. Systems that rely on the fog for their moisture, for their water. Here's an isotopic analysis, which I'll get into later in the course in biogeochemistry. Isotopic analysis is a major part of ecology today, and Berkeley's a leader in isotope research. A group on this campus in the Dawson lab performed studies where they looked at the isotopes of hydrogen in the water of fog and in rainfall. And you don't need to know the details for now. Just know that this is a variable that can characterize fog and rainfall differently based on their different hydrogen isotope ratios. Well, rainfall has a very low hydrogen isotope ratio. Fog has a very high isotope ratio. And you can go into the plants and check the water that's circulating in the plants and determine where they are getting their water based on these isotope ratios. And what you see is that in those summer months when it's so dry, the plants are getting a lot of their water from the fog. That's the deviation of this line from the rainwater values toward the fog values. In plants like rhododendrons and redwood trees, sequoia, rhododendron, and all the plants associated with these redwood forests, they're heavily reliant on fog in those summer months. You can grow such magnificent trees here in California because you have a fog input of water during the dry season. Otherwise, there wouldn't be, the availability of water would not be sufficient, and you would probably have just the shrublands rather than the great forests, like the redwood forests. Now the redwoods, they don't drink the fog directly, for the most part, through their leaves. They catch the fog and it drips down to their roots, and then they take it up by their roots. Now, chaparral, our beloved fog forests of redwoods, they don't even show up on here, I don't think, on the major terrestrial biomes of the world. They are not major, I guess. You know, those ecosystems I was talking about, well, yeah, it's here as woodland, shrubland. There's your fine boss of South Africa. There's some Australian Mediterranean conditions, your Mediterranean conditions around the Mediterranean Sea. I take it back, we're on here. Specifically, the input of fog isn't represented. These are some of the major biomes of the world and their distribution. We can define a biome as a major division of the communities of the Earth based on similarity of adaptation and physiognomy, particularly of the vegetation, but it corresponds oftentimes to the animal life as well. The deserts provide a great example of convergences in adaptation, not only of the vegetation, but of the animal life as well. And these are the biomes in the terrestrial environment. And I'm just going to review them very broadly. I'll use the words a lot, these different names of these different biomes. And when I use a term later in the semester, I just need to assume that you understand what I'm talking about. I've made that mistake in the past where I use a word like mangrove, which as we'll see is a good biome. And then I realize people don't know what a mangrove system is. So here we go. Again, in relation to precipitation and temperature are two major variables that determine vegetation structure in terrestrial environments. On a climograph, we look at precipitation in relation to temperature in this way. And we can see that the major biomes of the world fall out more or less neatly according to just those two variables. Now, it's not this neat. There's a lot of overlap. There's a lot of spill. But that gives you the broad idea of these connections. Temperate, let's take tropical rainforest. The tropical rainforest occurs in an area where temperature is relatively high on this end, and precipitation is high. So where it's hot and wet at the extreme, you're likely to see a rainforest, right? So that's how you read it. Where it's very cold and there's little precipitation, you're out here in the tundra, the frozen tundra. So let's review a few of these systems. Tropical rainforest. These are the systems that so excited Darwin and his generation when they left England and got on their boats and landed in equatorial Brazil and saw a system like this and thought, my gosh, I've been dreaming about something like this, but never have I seen such a thing, because it doesn't exist in Northern Europe. This profusion of vegetation, which is full of creatures and full of activity and really humid and even dark at the forest floor, because all the light is captured up in the canopy. Very little filters through until one of these massive trees breaks and falls, and with its liana attachments, these viney attachments, tears down a whole section of the forest and opens up a big gap where the sunlight pours in and finally reaches the forest floor. These things will erupt, and any seedlings here will grow toward the sun and fill in that gap. Classic rainforest type system, that one in Costa Rica. We have a version of rainforest in the temperate zone. It's at those latitudes of 60 north and 60 south, where the air cells are again rising and dropping their moisture. So if you go up to the Olympic Peninsula in Washington, Northern Oregon, Washington coast, British Columbia, you can see temperate rainforests. They're cooler, they're temperate, not tropical, but extremely high amounts of precipitation, leading to profuse vegetation again. Extremely tall trees, spectacular trees. I went for the first time in August to British Columbia. Beautiful country, all kinds of life, the decomposers included. Tropical dry forest, or tropical seasonal forest, also toward the equator, and tending to be warm, but seasonal in precipitation, seasonal in the amount of water available. And many of these trees will lose their leaves during a part of the year. They're deciduous, some of these trees. They'll drop their leaves to preserve moisture during the non-growing season. And many of these systems are very desirable places to live for people. So much of the tropical seasonal forests of the world have already been removed, cut, inhabited. A place like Central America, much of Mexico, would have been, was tropical seasonal forest, and now it's stripped and inhabited agriculturally or in terms of urban environments. So it's a system that's quite challenged. The savanna systems, a really interesting system. Spotty trees throughout, including a baobab here in Africa. Spotty trees in the middle of these grasslands. What's one of the abiotic factors that plays a role in sustaining systems like this? Anyone know a physical factor that plays a role in the maintenance of savannas? Storms, big storms? Yes, these things are characterized by, they can be characterized by spectacular storms, providing a fair amount of moisture, usually on a seasonal basis, to allow the growth of trees. What else? Yes? Fire is a big part of this. Recurrent fires that don't allow the woody vegetation to come to dominate and maintain the grassy physiognomy of this type of system. If you took the fire out of this system, it would change its physiognomy. A savanna would. And when you think about the African savanna and you think about human evolution and human use of fire, you can think back on the scale of 1 million years and the role that humans have played in the construction of ecosystems like this in places like Africa. Your seasonal forests, your temperate seasonal forests of the eastern US, for example, where you get your beautiful changes of color in the autumn. Again, deciduous trees that in the winter, even if there's precipitation in the form of snow, it's unusable precipitation for the plant. So the winter, if it's below freezing, is extremely arid from the perspective of the plants, even if it's snowing. And so that lack of water will lead to a cessation of growth, and the plants will drop their leaves in order to conserve energy and resources and be efficient for that season. They'll withdraw some of their resources before shedding their leaves. Temperate seasonal forests. And the fact that they drop their leaves in a deciduous forest like this has a big effect on the soil, because it can build up these massive layers of humus and decomposing material dropped by the plants. Grasslands in the temperate zone. Again, many of them influenced by fire. Many of these extremely fertile areas with great soils. And this is, has proven to be great farm country, great agricultural conditions in different parts of the world. Your deserts with their succulents in highly water-stressed environments, but don't think of a desert as just a barren area. Deserts are extremely rich with life, including animal life. The boreal forests of the north can have extraordinary biomass of plants, mostly conifer, mostly needle-leaved type plants, not your broad-leaved and deciduous types, but your needle-leaved types, better adapted to those cold growing conditions. In a place like this, in a place like the northern portions of North America where there's boreal forests, there's a lot of lakes and aquatic systems that influence them also. Some of them a function of the retreat of glaciers that left ice that melted to form this richly aquatic environment within the boreal forest zone. With so much biomass, so much carbon sequestered in these forests, they play a big role in global atmospheric dynamics. Boreal forests do. The tundra, even further north from the boreal forest. Boreal means north. Go even further north, and trees can't grow. The soils may indeed be frozen. There may be a permafrost, permanently frozen soils, and the trees can't survive. So you tend to have this herbaceous and lower growing vegetation characteristic of tundra. You're effectively above tree line. Some of you may have hiked up a high mountain and gotten above the trees, above tree line altitudinally. Well, this is really getting above tree line latitudinally. Quickly, we'll go over the aquatic biomes of the world. And just terminologically, the way I use aquatic is to include both freshwater and marine systems, as well as that sort of in-between condition of brackish waters. Sweetwater, saltwater, semi-sweet water. Brackish water is like, in an estuary where a river meets the sea. We'll see a couple of those types of systems. Somewhat salty, relatively high in dissolved mineral salts. So all of those I consider aquatic systems, although sometimes people just refer to freshwater systems as aquatic systems, and the others as marine. I include them both. So when we think about a lake, a good aquatic system, we need to divide it up for convenience and discussion, and limnologists, those who study lakes, limnologists, use this terminology all the time. It can be divided in terms of how deeply light penetrates, the photic zone, the light penetrating zone where photosynthesis is most likely to be occurring, and the aphotic zone where light attenuates and no longer penetrates the darker areas of the water column. Distance from shore and the depth of the water can distinguish between the littoral zone, the near shore, and the limnetic in a lake, further from the shore in deeper waters. And that littoral zone is characterized by vegetation that's implanted in the substrate, photosynthesizing there. A greater influence, perhaps, of the terrestrial environment, organisms that move between the two biomes at this edge, at this boundary, at this ecotone. And then we can also look in terms of the organisms and the environment of the substrate itself, the benthic zone, where the benthos, B-E-N-T-H-O-S, the benthos, that community of organisms lives in the benthic zone versus the pelagic zone, the open water zone. Helpful terms that will be repeated as we go through this course. You've all had a kid's book where you follow the little drop of water from the place where it falls on the mountain and it enters the stream at the headwaters of a river and flows down the river toward the ocean. And some of it may get into a lake system and pass through lakes, some of which may be oligotrophic, others eutrophic, depending on how many nutrients are available in the system. An oligotrophic lake has fewer nutrients, and visibility might be high because in lacking nutrients, it lacks much photosynthetic activity, and there's nothing in the water column to distort the view. When in a eutrophic lake, like this swamp, you can't see through because the nutrient loads are so high, there's so much physical activity, so much algae in the column, phytoplankton, zooplankton. Visibility is low. Wetlands in general, as aquatic systems, these may be fed by springs below ground. They may be fed by streams and rivers in a ponding area. A wetland is an area with standing water at least part of the year, and it may be all year long. It's a broad category, a wetland. When the rivers meet the sea, they do so at an estuary. And sometimes a river will meet the sea and expand out in this fractal network, which is a delta. And these systems are influenced both by marine processes, and they can be brackish, and tidal influences may influence such systems, but they're also full of nutrients from the land that's flowing down. Really rich ecosystems that are highly desired places to develop and look for food for human beings, deltas and estuaries, as well as the salt marshes on the coast with their marsh grasses and various vegetation adapted to those habitats. Again, tidally influenced, and these may be strictly marine if there's no freshwater source from land. It's maybe just a salt environment. Mangroves, these forests that can grow with their feet in the ocean water, where the tide, at high tide, may cover their roots, and they may be exposed at low tide. Fascinating systems. And we can divide marine systems in a similar way, and the terms basically overlap. The amount of light that penetrates, photic and aphotic, the distance from the shore, slightly different term here, neritic and oceanic, and your open water bottom, same thing, pelagic zone and benthic zone. Also have this neat intertidal zone. Lakes don't undergo tidal changes. oceans do. And in the ocean, in the marine zonation scheme, we have an intertidal. We also have an abyss with very deep ocean conditions where we may have hydrothermal vents. Vents like these, you can click this movie and watch a cool Planet Earth movie on the web about hydrothermal vents and the unique organisms that occupy those deep vents, fully out of range of sunlight penetration. Your intertidal zones, the intertidal is the zone between the highest tides and the lowest tides. And we have incredible intertidal ecosystems right here on shore, short drive away with their tide pooling opportunities. The coral reefs of the world, we'll talk a lot about coral reefs. Here's a distribution map of reefs. Extremely productive systems that can grow in extremely nutrient-poor environments. And that paradox of how you can get such a productive system in such a poor general area in terms of nutrients, something we'll discuss. Kelp, these brown algae that grow so magnificently off of California and cold water currents, a whole biome, a whole aquatic type of biome. Seagrasses. For those of you who want to stick around, let's watch a fun movie on seagrasses. For those who don't want to stick around, you can watch it on the web.